Hello all students, how are you? I hope you are well and safe at your home. In the last class of this chapter chemical bonding, we discussed about the MOT, Molecular Orbital Theory. But today I will tell you how to apply the MOT and find out the bond parameters. See, with the help of molecular orbital theory, we can find out the magnetic behavior of molecule, we can find out the bond order and also the existence or non-existence of the molecule. So how to calculate all these parameters which I told you right now. So let's start today's class of bond parameters by molecular orbital theory, and let us study all these topics. In this session, I will tell you about the molecular orbitals and their energies. In the previous session, we discussed that how these molecular orbitals are formed, what are the shape of the different molecular orbitals. But in today's session, I will tell you about the energies and how to fill these molecular orbitals. So the energy of the molecular orbital, it depends upon the two factors. Number one, nature of the atomic orbital, which is AO, from which it has been formed, which means nature of the atomic orbital from which this molecular orbital has been formed, and also the energy depends upon the extent of overlap, means the amount of mixing or overlapping between the AO. So when we already know that we discussed in the previous class, when AO combine with each other, they form MO, and the extent of overlap between the AO, it decides the energy of MO, molecular orbital. Now, what are the homonuclear diatomic molecules? Homonuclear diatomic molecules means, of course, they are diatomic, and the term homonuclear means both the atoms are of same type. So if both the atoms are of same type, students, it is called as homonuclear, right? So homonuclear diatomic molecule follow two type of orders while arranging the MO in the increasing order of energy. The one order is followed by up to nitrogen, lithium, beryllium, boron, carbon and nitrogen, and this order in this manner, where the least energy is of sigma 1s, then sigma star 1s. Remember, when we represent the star sign, this simply means ABMO, anti-bonding molecular orbital. You already know this. This we discussed in the previous session. So the least energy is sigma 1s, then sigma star 1s, then sigma 2s, sigma star 2s, then pi 2py and pi 2px. They have same energy. And then sigma 2pz have greater energy. Similarly, pi star 2py, pi star 2px, they have same energy. And then sigma star 2pz. So this is the order of energy up to nitrogen. What this order looks like exactly up to nitrogen? This order looks like this one. You see, this is the increasing order of energy. This is sigma 1s, sigma star 1s, sigma 2s. These are AO, atomic orbital, and these are MO, molecular orbital, out of which this is BMO and this is ABMO, anti-bonding. Again, this is BMO and this is ABMO. Again, these are BMO and these are ABMO. So this is how we arrange them in the increasing order of the energy. All right. So this is the order of energy for the MO, molecular orbitals, up to nitrogen. Now this sequence followed by oxygen, fluorine and neon. For the molecules like O2, F2 and neon and their derivatives, order of the energy of molecular orbital is not like similar to the previous one. Now they follow this order: sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, then sigma 2pz. There is a change in the order of energy in comparison to the previous one. Rest is same, and the order looks like this. See, here is the change in energy, where energy of sigma 2pz is lesser than pi 2px and pi 2py, and this order is followed by oxygen, fluorine and neon molecules. Alright. Now, if you compare side by side This is the MO energy level diagram up to nitrogen, and this is above nitrogen for O2, F2 and Ne2. You can see rest all energy levels are same apart from this one. As I told you earlier, there is a change in the energy order in the 𝝅2px, 𝝅2py and �sigma2pz, and that too is because of the repulsion between the orbitals. In case of the O2, F2 and Ne2, there is a repulsion between these non-bonding molecular orbitals, and because of this repulsion there is a change in the order of energy. So in writing, what is the difference between the molecular energy level in two diagrams? In case of Li2, Be2, B2, C2, N2, the difference in energy of 2s and 2pz orbital is small. Hence they can interact with each other as they have a small difference of energy. But in case of O2, F2 and Ne2, the difference in the energy of 2s and 2pz orbital is large. Hence they cannot interact with each other. So there will be less interaction, or you say no interaction, between 2s and 2pz for these higher molecules. Alright, so that was the reason for the change in the energy order. Now I shall tell you how to fill these MO. Students, why we formed MO? We formed MO to explain the bonding and the magnetic behavior of the substances. So now we have some certain rules for the filling of molecular orbitals. Rule number 1. In the molecular orbitals, electrons are filled in the increasing order of energies as like the other molecules or atoms of the species, and that too is in the compliance of the above principle, which simply means molecular orbitals having the lowest energy is filled first. The MO, which is lowest in energy, will receive the electron first, and this is also above principle. Now in the above principle, according to the Pauli's exclusion principle, how many electrons we accommodate in any orbital? I'm talking about the atomic orbitals while we study the valence bond theory. The answer was 2. Same here. Each MO molecular orbital, it can accommodate maximum of 2 electrons. It can accommodate maximum of 2 electrons, that too if they have opposite spin, according to the Pauli's exclusion principle. According to the Pauli's exclusion principle, if they have opposite spin, only then they can accommodate maximum of 2 electrons. Now if there are more molecular orbitals of the same energy, these are first singly filled and then pairing starts as per the Hund rule. As per the Hund, if 2 molecular orbitals have same energy, then both of them will receive 1 electron first of the same spin. Only then pairing will take place. If you do it like this, if you fill 2 electrons like this is wrong. This one is right. And if you will fill 2 electrons in the same energy level of 2 different molecular orbitals like this one, this is also wrong, right? According to the Hund's rule. Now we will draw some MO diagrams. Say for example, this is the MO diagram of H2 plus ion. In the H2 plus ion, how many electrons? Each hydrogen contain 1 electron. So H2 should have 2 electrons, but since it has positive charge, 1 electron is lost already. So the total number of electron is just 1, and this 1 electron will be filled in sigma 1s orbital, and this sigma star 1s and the remaining higher molecular orbitals, they will remain empty. In the H2 molecule, there are 2 electrons which will be filled in this manner. Both of the electrons will enter in the sigma 1s molecular orbital, which is also BMO. Now what about the H2 minus ion? See, H2 has 2 electrons, and in the H2 minus ion there is 1 additional minus charge, because of which there are 3 electrons. So now these 3 electrons will be filled like this. 2 electrons in 1s, sigma 1s, and 1 electron will be in sigma star 1s. If you will accommodate 1 more electron, it will be accommodated in sigma star 1s and then in the higher molecular orbitals. So this is how we fill the MO. in the increasing order of energy. In the each MO diagram, you can see this is the increasing order of energy. So electron is first received by the lower energy molecular orbital, but once it is filled, electron is then filled in the higher energy orbitals. Now how to calculate the bond order? With the help of MO diagram, we can always calculate the bond order. There is a formula how to calculate the bond order. Bond order is calculated like 1 by 2 into number of electrons in BMO minus number of electrons in ABMO. How many total electrons are there in BMO minus how many total electrons are there in ABMO, and the subtraction is finally divided by 2. That 2 is equals to bond order, right? So if someday you have to calculate the bond order, what you need is first you should calculate how many electrons are there in BMO, then you calculate how many electrons are there in BMO, and then you subtract number of electron in BMO and ABMO, and then divide the figure by 2, and then you will get the bond order, right? We will solve some examples in this class. Suppose, say for example, we have O2 minus ion, right? How many electrons are there in O2 minus ion, which is also superoxide? O2 minus ion is also called as superoxide ion. Each oxygen is having 8 electrons. So total there are 16 electrons, including this -1 charge. There will be 17 electrons altogether, right? And according to the molecular orbital theory and according to the MO diagram, the electronic configuration of O2 minus ion as per the MO diagram, you know the MO diagram of O2, this was the MO diagram of O2. Now say for example, if you have to fill the 17 electrons in this MO diagram, how you will do that? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now since these two having same energy, 11 and 12, 13 and 14, 16 and 17, and one more electron is there. So these are 16 electrons, and now 17th electron will enter here. So how many unpaired electrons are there in O2? Only O2 minus is 1. Now the same MO diagram you will see here in this. This is the same MO diagram. This KK means sigma 1s and sigma star 1s, sigma 2s2, sigma star 2s2, sigma 2pz2, and then finally this is the electronic configuration. Now the bond order will be number of electrons in BMO minus ABMO, that is 8 minus 5 for the outer shell, because for the inners they are cancelled out with each other, divided by 2. Furthermore, it goes 1.5. So now we can say with the proof, we can say with the authority that O2 minus is paramagnetic because it contains one unpaired electron, which I have already shown you in the MO diagram in the previous slides. So now we can say this with the authority that O2 minus is paramagnetic, bond order is 1.5, and it is having one unpaired electron. Now what is the benefit of calculating bond order? So there are some significance of calculation of the bond order, right? First is stability of molecule. Once you calculate the bond order, you can have an idea of stability of molecule. Also you can calculate number of covalent bonds. With the help of bond order, you can also get the idea of bond length. Greater the bond order, lesser will be the bond length. Also you will get the magnetic character, that whether compound is paramagnetic or it is diamagnetic, what kind of nature it is having, and you can also calculate the bond dissociation energy. When you have to find out the stability of molecule, see, by the calculating bond order of a molecule, you can also check the stability. If number of electron in BMO, NB is the number of electron in BMO, if it is greater than ABMO, then molecule is stable and bond order will be positive. If number of electron in BMO is lesser than ABMO, then molecule is unstable. Why it is unstable? Because in this case bond order will be negative and the molecule will be unstable. But if number of electron in BMO is equal to the number of electron in ABMO, then bond order will be 0. In this case also molecule is unstable. You can say that it does not exist. So whenever students bond order is 0, Whenever bond order is 0, you can say that molecule or the species, whichever is there, does not exist, right? Another one is bond length. Bond order also helps us in predicting the bond length. Bond order is inversely proportional. It is inversely proportional to the bond length. I also told you this few moments back. Greater the bond order, lesser will be the bond length. So higher the bond order, shorter is the bond length. Bond dissociation energy. See, what is bond order? Simply, in simple words, bond order is the number of bonds between two atoms, right? So if there are more number of bonds between two atoms, it will be more difficult to break that bond particularly, and bond dissociation energy will be more. So bond order is directly proportional to the bond dissociation energy. Greater the bond order, greater will be the bond dissociation energy. So the higher value of bond order, greater is the dissociation energy of the molecule. Here are few examples. In this example, you see for oxygen molecule, bond order is 2. This is the bond length, and here is the bond energy. Now in the nitrogen molecule, bond order becomes 3. Now you see bond length becomes less, although they are different atoms. Oxygen and nitrogen are not same atoms, so technically it is not a very good idea to compare their bond length. We always compare bond length when species are same. But still, in nitrogen there are 3 bonds, so bond length is less. And because of these 3 bonds, you see what a great difference in the bond energy. The bond dissociation energy of nitrogen is 945 kilojoule per mole, while the same bond dissociation energy for oxygen is just 495 kilojoule per mole. Number of covalent bond. Bond order in molecule is equal to the number of covalent bond holds between the atom in that particular molecule or the species. The bond order provides us a qualitative comparison, qualitative, not the quantitative, but the qualitative comparison of the bond length and bond strength, bond energy that is, and no quantitative calculations are possible with the help of bond order. So it gives you the qualitative comparison. Alright. Now with the help of MO diagram, that is molecular orbital diagram, you can also have the idea of magnetic character. We know that by and large, on the basis of number of unpaired electrons or the presence or the absence of the unpaired electrons, compounds magnetically they are of 2 types. One is diamagnetic. If all the electrons are paired in the electronic configuration of the molecule, then that molecule is said to be diamagnetic in nature, which is repelled by the magnetic field we studied in the different chapters. Paramagnetism or the paramagnetic behavior. If all electrons are not paired, then molecule will have one or more unpaired electron. Then this molecule is said to be paramagnetic, and it is attracted by the magnetic field lines. More are the unpaired electron, higher is the paramagnetism. See, the amount of paramagnetism, you say the quantity of the paramagnetism, it depends upon the number of unpaired electron. More number of unpaired electron, more will be the paramagnetic character. Say for example helium molecule. Now if you imagine the helium molecule, how many electrons are there in one helium atom? Each helium atom contains 2 electrons. So if you suppose He2 molecule, there will be 4 electrons, and those 4 electrons will be filled like this: 2 electrons in sigma 1s and 2 electrons in sigma star 1s. Now how many electrons in BMO? 2. And how many electrons in ABMO? Again 2. And this will be the electronic configuration of He2 molecule. Sigma 1s BMO contain 2 electrons, and sigma star 1s antibonding will also contain 2 electrons. These are the atomic orbitals, belongs to atom, and these are the molecular orbitals, belongs to the molecule. And here will be the bond order. Number of electron in BMO 2, number of electron in ABMO 2, bond order will be absolute 0. So the summary of the story, if bond order is 0, we say that helium 2 molecule does not exist. Now there is no point of discussing another properties of helium-2 because it does not exist. And when it does not exist, there is no point of discussion. So bond order is 0, which means no bond exists between the helium atoms. The electrons of anti-bonding molecular orbitals cancels the stability gained by the electrons of BMO. So whatever the stability which was gained by the electrons of BMO, in this case of He2 molecule, it is absolutely cancelled by the electrons of ABMO, and in total bond order becomes 0. Now what about the Li2 molecule? Lithium. Each lithium contains 3 electrons. So obviously Li2 will have 6 electrons, and the electronic configuration of Li2 will be like this. Now this above configuration, it could be written like this. Kk star means 2 electrons in sigma 1s and then 2 in sigma star 1s, and then remaining 2 electrons are in sigma 2s. You can also write down the MO diagram in short like this. This is sigma 1s, sigma star 1s, this is sigma 2s. How many electrons are there? They are MO. I'm not drawing the AO here. How many electrons are there? 6 electrons. So they will be filled like this: 1, 2, 3 and 4, 5 and 6. As the inner closed K shell do not take part in bonding, therefore they are called as non-bonding orbitals. So this will be drawn like this. As I told you, 2 electrons in sigma 1s, 2 in sigma star 1s, and 2 electrons in sigma 2s. Alright. So this is the MO diagram of the Li2 molecule. What will you conclude? With the help of this MO diagram, you see there are 4 electrons in BMO and there are 2 electrons in ABMO. So bond order will be 1. And do you see any unpaired electron here? These electrons are paired, paired, paired. So all 6 electrons are paired. No unpaired electron is present here. So there is no unpaired electron, hence it is diamagnetic in nature. So Li2 molecule is stable because the bond order is 1, but it is diamagnetic. This is also a kind of drawback of molecular orbital theory, because if you see, according to the MOT, bond order of Li2 is 1. So it is stable theoretically, but in real life you will never see Li2 molecule. Its existence is proved by the MOT, but in real life, in the practical situation, does not exist. This is one of the drawback of molecular orbital theory. Now if you compare some molecules according to the MOT, like Be2 or the B2 or the C2, and if you form the MO diagram and you fill the electron in them, this will be their MO electronic configuration. Students, according to this configuration, their bond order will be 0 in case of Be2, 1 in case of B2, and 1 in case of C2. Also, when bond order is 0, this molecule does not exist. When bond order is 1, yes, it do exist, and it will be paramagnetic because of the 2 unpaired electrons. These 2 electrons you see, they are unpaired. Here all electrons are paired. No unpaired electron is there in case of C2, so it is diamagnetic. So molecular orbital theory excellently explain the bond order, bond length, and also magnetic behavior. Now this is the bond order of N2. You see in this bond order of N2, if you draw the bond order of N2, how many electrons are there? In the N2 there are 14 electrons altogether, 7 from each nitrogen. So it will be total 14. You see these 14 electrons are filled in this manner: 2 and 2, 4, 6, 8, then 4 electrons are here, 12, and 2 electrons are here. So number of electrons in BMO will be 2 and 2, 4 and 6, 10, and number of electrons in ABMO will be 4. So here in this case, bond order will be 10 minus 4 divided by 2, that is 6 by 2, is 3. We all know that bond order of nitrogen is 3 and it is not having any unpaired electron. Since all electron of nitrogen are paired, it is diamagnetic in nature. And these are the characteristics and the different bond orders of the nitrogen and its derivatives, ions. This N2, N2 plus, N2 minus, N2 minus 2, bond order is 3, 2.5, 2.5 and 2. Stability is also proportional to the bond order, and it is inversely proportional to the number of electron in ABMO, because you know those electrons which are present in ABMO, they have higher in energy, they are higher in energy, and because of the high energy they destabilize the molecule. And magnetic character, we judge it by the number of paired or unpaired electrons, whether they are present or not. And this is the order of the relative stabilities of the N2, N2 plus, N2 minus and N2 minus 2. So this is all about the order of bond, bond energy, stability and bond length that we discussed in this unit. In the coming class, we will tell you more about the chemical bonding and the structure of the compounds. In this today's class, we will keep it up to here only, and I hope that all the topics which I taught you today are well understood by you. Please keep coming and keep studying. Thank you.